instrument. All right, thank you. First of all, thank you for having me. Thank you to the organizers to asking me to come here. I'm very happy. It's my first time. I'm happy to be in sunny California, I guess. All right, so my talk is going to be entirely about correlations in gravitational waves data. Because of the previous talks, I can skip some of the background material to conserve the overall time. This is a very quick outline. I will give a quick introduction about, or a reminder, not very much needed, about what it is that we want to do and how we can do it. And then go through an incomplete story of measurements of correlations in gravitational wave data in the last 10 years. Disclaimer, I have a very young daughter. She doesn't like to sleep, and so neither do we. And so sorry if I forgot your favorite measurements or paper. Just let me know, and I'm going to update it. All right, so first of all, what do we want to do? I guess we all agree we would like to learn what channels contribute to the compel binaries that we're seeing in LVK data, found either by the LVK or outside groups, and measure the relative abundances, if more than one of them is contributing signals, what the properties are of the individual channels, and dare I ask, in an accurate way, right? To me, that's a very important point. And now, the reason why I'm here is that I want to make a pitch that in pursuing this goal, astrophysical correlations in each population have a significant role to play. The reason being that two populations or two channels that may make similar prediction on their marginals may still be easier to distinguish in higher dimension. And so we should stop looking at marginal plots only. And I say this hating corner plots. All right, so how do we do it? Aditya said something about this already. Let me very quickly review. There are a few ways. One that was not stressed earlier today is that we could try to directly use the output of PopSynth, right? The truth is that now in 2025, thanks to the work of many of you really, we have theoretical and numerical simulations that can predict the properties of compact binaries, or the properties that a compact binary should have, depending on where it forms. And this is either numerical simulations or theory. And so our job theoretically is very simple. We just have to compare those predictions with the data that we are collecting. Now the caveat is that the simulations are costly, and hence they don't capture all the physics. We don't have an infinite number of them. So it's a tricky business. And in spite of this, you can try. And to my knowledge, Mike was the first person who showed this. What Mike has done in a paper a few years ago, when we were all younger, is it took basically output of PopSynth for 3 field scenarios: common envelope, chemical homogeneous evolution, stable mass transfer, and 2 dynamical formation scenario, globular and nuclear star cluster. For each of these, he obtained basically the distribution of things like mass ratio, redshift, and effective spin, based on some knobs, for example, the fraction of the envelope that is removed or retained, and the black hole spin at birth. And so you can put this data in a grid where you have, for example, these 2 knobs, and in each grid point you have the predictions, in this case, for example, for the shear mass, from these 5 channels. And so what you can do then is to compare these predictions with the data, either moving on the sparse grid. It has to be sparse, again, because those simulations are expensive, or more recently using machine learning emulators to interpolate. And that works. In his paper, Mike, for example, found using GWTC2 data that at least 2 channels are required. And that's great. When I saw this paper, I was very excited. And, there are caveats, though, we should be aware. And for example, the most obvious one is that those, results coming from PopSynth are just, rough approximations of nature, just because these simulations are very expensive to perform, as we have heard this morning. And, in fairness, we're not even likely to have a complete set of astrophysical models. And in a paper led by a former undergraduate at MIT, and also with Mike, we show how both of these factors can result in significant biases. Okay, so what else can we do? As we heard today from Aditya, we can use phenomenological models. The idea here is that we can exploit some, at least, basic expectation based on theory of what our mass or spin or redshift distribution should be, and make a simple parametric model based on those. For example, as we heard earlier, for the mass function of black holes, you may expect an underlying power law, you may expect a bunch of Gaussians, and a mixture of these can be your model, and you measure the parameters from the data. I will, of course, skip all of the technical details about selection effects. You can ask Reed or Ilya or me or others. Right. Another way which we have also heard about goes under different names. One of them is agnostic models or weak model or non-parametric models, even though they have even more parameters normally. So this approach allows you to basically model or match more complicated distributions than a power law or a Gaussian or whatever. There is a very long menu of approaches you can follow, and it's growing every day. One that you've heard about earlier, using splines. This, for example, is in a paper by Bruce Edelman. You can use cubic spline either by themselves or as a mixture on top of a strong model like a power law. So you have a base model which is strong, and the spline can add some wiggle on top of that. You can use autoregressive model. You can use a Gaussian mixture model. You can use Gaussian processes. Ilya wrote a great paper a few years ago that used those. And again, there are new ideas every day. Gaussian process, the very basic idea is very simple. You bin your parameter space, and the parameter you're measuring is basically the rate in each bin as a function of, say, 2 parameters, M1 and M2, or whatever. All right. So all of these are possible avenues. Here is my controversial table about what they can do for us, especially focusing on correlations. I have pop-synth approach models, strong models, agnostic models. So the thing I care about for today is, are correlation easy to implement in each of these approaches? For pop-synth, they're just built in. As long as you believe the pop-synth, of course, output, the correlations are already there. For strong model, you can bake them in, although it's higher to do this in higher dimensionality. And for agnostic model, it can be pretty easy, especially with Gaussian processes. Whether they're easy to interpret, it's also a raging debate in my community. The pop-synth models, of course, are trivial to interpret. The strong model also, if you believe the model, if the model is good, it is non-trivial if you use agnostic models like splines or Gaussian processes. The last row I think is very important. We should talk about it more often. The risk of biases, I think it's very large if you use pop-synth models or strong models. It's smaller for probably agnostic models, but again, usually at the expense of interpretability. Okay, so with this, kind of quick summary and introduction mainly to set up the terminology, let me quickly review with you what has been happening in the last 10 years. So let me start with the first few years. Again, I'm focusing about correlation specifically. So one thing I want to stress is that up to the O3A catalog, or GWTC2, the LVK in the models we use in our papers did not explicitly include correlated models, perhaps with the exception of the mass pairing function, and I think Amanda may talk about it more later in the workshop. Interestingly, there was a 2020 paper by Mohammad Safarzad, I think Will was also there, and Enrico was there, where they analyzed the 10 binary black hole of GWTC1, allowing for a linear correlation between chi effective and 1, and found very mild/weak evidence. It was a very courageous thing to do with 10 binary black holes, though, in fairness. Right. Things changed as we started having more than 10 binary black holes. As far as I know, the first solid hints started appearing in 2021. In a paper led by Tom Callister, we allowed for the mass ratio in chi effective to be linearly correlated. And using this model on the 45 binary black hole of GWTC2, we obtain the results you see here in the plot. X is mass ratio, equal mass, unequal mass. The y-axis is the mean of the effective spin. And basically you see median and 90% uncertainty. This plot tells you that there are more positive chi effective at more unequal mass ratios. And of course this was exciting because it was not something that was trivially expected from pop-synth. There has been a lot of work since to explain how you could get this, maybe from AGNs. I should also say that these findings that were originally again based on 45 binary black holes have been later confirmed by the LVK with the 69 binary black hole of GWTC3 and the 150-ish of GWTC4 with a caveat that I'm going to discuss later. Another paper used a linear correlated model for chi effective and the redshift. This was led by a former student of mine, Silvia Biscoveno. And in that paper, we reported, we found basically that the distribution, the astrophysical distribution of chi-effective broadens with redshift while it stays centered roughly around 0. This is shown in this plot here, where the x-axis is chi-effective, from -1 to 1, with cartoons that help you understand what chi-effective means. And the y-axis is the probability. This is on GWTC3 data. Different colors are slices of the chi-effective distribution at different redshift, and you see that a very, basically, nearby redshift, it's very narrow, and then it broadens as you go farther and farther. And again, there's been some very nice papers about why you can obtain maybe something like this, depending on how metallicity, which evolves, of course, with redshift, that affects your spins. And I should also say this was confirmed also by the LBK paper, again, in GWTC4. Okay, this is great. I love this. I was involved in this work. However, as a data analyst, I always have to ask myself, because these are pretty strong models, these are linear correlation on top of Gaussian distributions, am I torturing the data? Right? There is a saying that if you torture the data enough, it will confess, right? And so these models are doubly strongly. The base model for chi-effective is a normal, and the correlation is linear, right? And so this is the math if you care. For example, for chi-q, again, the base model for chi-effective is a normal, and I'm allowing the mean, the location, and sigma to vary linearly with q. And this is probably okay, as long as the size of my catalog is small enough that it will not pay the price for eventual model, violence on my data. However, over the last few years, I've been thinking and working on ways how to, relax a bit some of these strong assumptions. In a paper led by a student, Jack Hensel at MIT, we relaxed at least the linear dependence in the following way. We left the base model still a Gaussian, but we relaxed the assumption of linearity in the correlation by making it basically a spline correlation. So the mean and, say, standard deviation of your chi-effective distribution could be a function of z or q, but that function doesn't have to be a line anymore. It could be a wiggle, right? And in this plot here, where I have, for example, chi-effective versus redshift, on GWTC3, for example, Jack has shown us if you use this more elastic spline correlation, you get the results that overall agree within the very generous uncertainties, right? However, projecting to a catalog of 400 simulated sources, as we may have, or definitely will have at the end of O4, especially because O4 is now longer than ever before, if you assume some true underlying universe which has a nonlinear correlation, then your linear model in blue and your spline correlated model in yellow will start to disagree at more than their statistical uncertainties, which, again, it's something that we have to pay attention to, in my opinion. Okay, great. So with this in mind, let me tell you where we are now with the latest catalog. Aditya covered most of what we have found today, or a lot, but not these things. He nicely left them for me to cover. So let me quickly review for you the situation for Q chi-effective correlation in GWTC4. So this is the paper that came out a couple of months ago. In the latest paper, the LBK has used a combination of strong correlated 2D Q chi models, the linear and spline model I already introduced, and something else called the copula model based on a paper by Chris and Eric Train. And what we have found, summarizing this paper here, is that there is still evidence that something is evolving, but it's not clear anymore whether it's the mean or the standard deviation. So in this plot by the LBK paper, I have basically the slope of your location parameter and width parameter of this correlation. 0, 0 would be no correlation. And you can see in orange the results from the linear model, and in blue from the spline model. And you see that overall they want to be away from 0, even though especially for the spline is not excluded 100%. But it's not clear anymore whether it's the width that is changing or the location or both. So I personally would want to wait for more data to understand what's happening in here. On the other end, the results from GWTC3 are pretty much confirmed for chi versus redshift. Again, we use several models, and it is still the case that the width of the effective spin distribution increases with redshift. So it used to be easier earlier in the universe to get larger chi-effectives. Here you have on the x-axis the redshift, on the y-axis the mean of chi-effective as a function of z, and the width. Orange is the linear model, blue is the spline correlated model. You see basically they agree on no correlation for the location parameter, while for the width they both get some increase as you go away from redshift of 0. They start disagreeing, but so do their uncertainty at larger redshifts. I like this plot because they have plotted this line here. This line here, Aditya can correct me if I'm wrong, is the line at redshift above which we have less than 5% of our P samples, so basically very little information from the data. I like this because it tells you that you should not believe the linear model, because the linear model is a line, so it will hook on your data here and then keep going that way, even in regions where you don't have a lot of P samples at that point. Okay, very good. What else has been happening? The most, in my opinion, exciting recent development have been the introduction of a more generic way of capturing those correlations that don't even assume, for example, that anything is Gaussian or an underlying base distribution is Gaussian. There have been several proposed approaches in the literature in the last few years based on mixture models, on Gaussian processes, for example. And both of those approaches have been incorporated by the LBK in this catalog. We have seen the plot on top earlier today. This is M1 versus M2. Sorry, the y-axis got cut. We can forget about the blue half of the histogram. The orange and black is just the merger rate as a function of M1 and M2. And this is using a bin Gaussian process. The bottom panel shows the same kind of measurement using this mixture model, Vamana, which is a mixture of strong pieces like power laws and Gaussians and so on and so forth. Overall, they agree, which is nice. Okay, so in my opinion, and it's 5 p.m., I probably want to be controversial, the future is in this direction. We should stop or, kind of reducing our dependence on strong models. So at MIT, we have been working in the last couple of years on developing something that we call pixel pop. It's a higher resolution, high dimensional agnostic approach to population inference. It's based on Gaussian processes. This literally, since Ilya's in the audience, started with me pointing my student Jack Ainsel to your multi-notice paper. Say, Ilya's pretty smart. Can we do any better? Actually, it's not, yes, done a bit better on that, which is great. Actually, I think we sent you the paper, right, at some point. Very good. So we have run it both on software injections to check that everything works fine, and so there's the theory paper here, and also on GWTC3, so on the old catalog. And for example, this is a plot that I added after this morning discussion. Someone asked about whether chi-effective being negative can be a feature of our model being strong. I think this plot shows that is not the case. This on the x-axis are redshift, on the y-axis chi-effective, and the bluer your bins, the higher the measure rate. And again, this comes from this model, pixel pop, which basically assumes nothing else than a vague sense of continuity. So there is no underlying strong assumption being made. And then you see the marginals. In particular, you see that indeed we find that if we slice this at z of 0.1 and at z of 0.75, we get that the distribution of chi-effective is broadening with redshift. So this is all published. It's nice. It works. We have more recently been working with the GWTC4 data. This is not public. This is not in the LIGO data paper, I should say. We are writing our own follow-up paper. But just to give you an idea of what I mean by high resolution, this is the plot in the LBK paper. This is what we can do with pixel pop on the same data. And hopefully you should be impressed by the much higher resolution, which will allow you, when the number of detection increases, to resolve finer, potentially finer details in our underlying distribution. And again, I want to stress that nothing here is being assumed about how those two parameters are correlated, if they are correlated. We can already run this with 3 correlated parameters, and we are, again, as I said, assuming nothing but smoothness on the underlying distribution. If you look at marginals, which we have, we obtain and we compare with the LBK models, the bin Gaussian process and the full top, if you know what I'm talking about. pixel pop agrees with the other, agnostic approach used by the LBK, which is always reassuring. I also want to say that this logo is actually obtained sampling the logo with pixel pop. And that's something that Jack has done. My idea was something that probably would have got all sued. It was to do this. But then I watched an episode of John Oliver and discovered that Disney doesn't have a lot of sense of humor when it comes to, copyrights. And so we went with that one instead. That's my first and best use of Photoshop. I'm very proud of it. Okay, very good. The last few minutes of my talk, I want to talk about something which I think it's nice and I'm quite proud about. And that is the fact that we have shown in a paper led by Sofia Alvarez-Lopez how with pixel pop we can measure in an unbiased way the population parameters of a population which is non-trivial, meaning not heuristic, not made up by me, with power laws and peaks or whatever, but actually born of pop-synth results. Okay, so specifically what we have done in this paper is to take 400 binary black holes coming from common envelope defined as basically the output of Mike Zemin's paper. And I want to stress, so those black holes have masses, redshift, and chi-effective, which are highly non-correlated in ID. This is shown in this corner plot. This is the distribution of the true MQ chi-effective at Z of this population. And you can see it's basically a mess. If you just throw, your, simple power law peaks, of course, on this it will fail miserably, meaning it will give you entirely biased results. Right, so this is also shown in this matrix here, which is basically representing for the pair of parameters what their correlation is. It's scaled from 0 to 1. 0 means they're not correlated. 1 means they're maximally correlated. And so, for example, this tells you that M1 and Q are very correlated, then M1 and chi, Q and chi, and chi and Z, pretty much everything. Okay, so again, this would be a very hard problem to address with traditional, population analysis. So what we have done in this paper, also for pedagogical reasons, is actually approach this step by step. The first thing that we have done is to show that if you use a simple 2D correlation, you will get biased results. So what I mean here is that first we have modeled the NQ pair with pixel pop, so with an arbitrary correlation, but we left Z and chi-effective alone using a strong power law for Z and something more complicated for chi-effective that I can discuss later. And these are the results. If you look at MQ, this is the 2D, dashed line is the 90% of the truth, and here is the actual truth. And the blue, again, it's our measurement. If you look at the 2D and the marginal, it looks beautiful. And again, it's a non-very trivial correlation. I was very happy when I saw this. I can explain later if you are curious why we disagree here in the low mass ratio or low masses regime. But then if you look at what happens to your chi-effective distribution, dashed line is the truth, blue is your measurement, you are off. You can already see the error bars here, maybe you can there, but you're really off by way more than your 90% uncertainty. What's happening here? What's happening is that in reality, chi-effective was also very correlated with the mass and the mass ratio, but your 2D model doesn't know about it. So because we can run pixel pop in 3 correlated dimensions, we actually have done that. We added chi-effective to the correlated part, now leaving only Z alone, and that's better, but it's still not enough. So these are now slices of pairwise of parameters from my 3D correlated pixel pop cube. And so you have M1Q, chi M1, chi Q. It looks overall great. If you squint, you can see some small things that I can discuss. Maybe not today because we have the bus, but anytime in the next few days. But again, if you look at the chi-effective and you squint, you still see some issues here. Okay, not great. So the next obvious step would have been to run with a 4-dimensional pixel pop, where you just model everything in an unmodeled fashion, allowing for arbitrary correlation. We cannot quite do that yet. I'm happy to discuss this later. We have used something we call an hybrid pixel pop model, where we have still only included M1, Q, and chi-effective in the correlated part of the model. But for Z, now we have basically by hand correlated with the next most correlated parameter with Z, that was chi-effective. And if you do that, you get basically now you do better. Basically, this bias starts going away. It's not perfect because this is not a perfect model, but it goes in the right direction. And you can ask me about this later because here we have been cheating a bit to do this. Okay, how am I doing with time? I have 5 minutes, so plenty of time. Okay, one thing I want to discuss, this is also something I added in light of what Like was saying, it's something that it's close to my heart, it's the following question. If I use this weak agnostic model, which I don't have beautiful parameters like the slope of the power load, the branching ratio, right? Can I actually say something about formation channels, branching ratios? Can I understand where my black holes come from? And it's less trivial to answer those questions using those weak models. Something that we have tried is to use the output of this pixel pop hybrid analysis to measure at least some idea of similarity between the common envelope predictions, which where our black holes were drawn from, so the truth in quote, and the other two field channels from Zevin et al., which will be chemical homogeneous evolution and stable mass transfer. Here you see the distribution of the true values for mass ratio, K effective, and Z for these three channels, again from Mike's paper. I'm showing this mainly to stress, if I need, that chemical homogeneous evolution makes predictions which are much more different than CE and SMT, right? It's the most different of these three. And so you can calculate a quantity which is called similarity. Again, I don't need to go into details, and produce a plot like this, which has, again, very complicated. In this plot, if you are below this white line, common envelope, it's preferred over the alternative. If you are above the line, is disfavored. In other words, this plot is telling me that because CHE is here way down, I am pretty confident that not all of my sources came from CHE, which is correct because they all came from CE. But for SMT, the fact that that's on the diagonal pretty much implies that I cannot absolutely say with any degree of confidence that not all of my sources came from SMT as opposed to CE. And I want to stress, again, in light of early discussion today, that depending on which papers you have read in the last few months and years, this statement may seem much more depressing. However, that's because we are not making strong assumptions pretty much in here. Okay, we are assuming we know very little, and the price to pay is that we know very little at the end. Okay, but the risk of biases is lower. Yes, okay, beautiful. Next steps. So we're working on a few things. One is to work on having a 4D correlated model, which would be great because then you can put all of M1, Q, K effective, and Z. The main issue, for those of you who are curious, is actually the sensitivity, the BT. You can ask me about it later. Something I want to talk about for the next couple of minutes is something that we are doing, working on mixture models of pixel pop together with your strong model, which maybe can give us the best of both worlds. And the idea is that the strong model can do its magic, like it can give you power laws and peaks and slopes, and maybe pixel pop can do the dirty work of getting glitches or outliers or oddballs or the correlations that your strong model doesn't know about. And this is something I added because of the discussion between Teja and one of our speakers earlier about 1908-14, which we always leave out because we don't know what to do with it. We can do something with it because I can run pixel pop together with the GWTC3 LVK model, but this time without excluding 1908-14. And if I do that, Teja, this is the plot, I don't know where you are, that I promised you, right? This is the merger rate as a function of M1. I have here 3 set of curves. The pink is the parametric, it's basically LVK power law peak. The blue is the pixel pop contribution and the overall thing. Not very impressive. The rate increases a bit here. It becomes more impressive if you look at the pixel pop part only in the M1, M2 plane. You see this blue blob here, and sure enough, if you put the posterior of 1914, it's there. So basically what this is doing is that the pixel pop part, it's getting for you 1914 and making so that the strong model doesn't get biases, or doesn't pay a price for it. Okay, I'm still doing great with time because I only have 1 slide left. Conclusion, so I think correlations are the future. The future is correlated, I will say. And we are really start to see evidence that some parameters are correlated. And we are still unfortunately in a situation where a lot of our models are too strong, in my opinion. And we have no reason to believe that the universe is so simple to give us linear correlation or anything like that. Work is needed to develop idea resolution analysis, and in my opinion, Pixel Pop is a step in the right direction, not the only work in the community, I should say, by all means. And also let me say that Jack, who was behind Pixel Pop, is the person who really put this together, is applying for a job this year. You should hire him. And also because I have 10 seconds, and someone mentioned earlier that we are 10 years past 1914, and being from MIT, let me put up a slide to remember Ray. We lost him a couple of months ago. If you have not read this, there is a very nice New York Times obituary that you should be reading. It was great. I'm sure you would have loved a workshop like this. Thank you.
Great. Thank you so much, Salvo.
Can you go to slide 28?
8? 20? Yes, I can. May take a second. Oh, wow. Sorry. I clicked too many times.
28.
Oh, yeah. Sorry. I know. It's just there is a lag. So I click so many. I'm an Italian. Like when the elevator doesn't arrive, I click more times. That's why the first time I went to Japan, I was disappointed because in Japan, if you click again, you cancel the previous call. In Italy, that would never work. Okay, very good. There we are.
So, in your true model, this is an injected model, there are hardly any negative spins. And then persistently, you see a tail of negative spins.
Yeah.
So, do you, why is this happening, and do you worry if it's happening in the real data, because this is very important, right?
Of course. Okay, so thank you very much. That's a fantastic question. So for people in Zoom or recording, this was Teja, and the question is about the tail negative K effective. Okay, so this was something that was hinting up earlier when I said I know what's happening in the MQ. It's the same story. So this is a generic feature of agnostic model, is that because they don't make strong assumption, in a regime where the rates are very low, meaning they are so low that seeing one event or zero events are basically both possible, it's very hard to distinguish between 0 or 10 to the minus 9 or 18. And so what happens is that, in general, for weak models, in region where you don't have a lot of data, the uncertainties blow up. And now the next question is, though, why don't the error bar here go down, or the uncertainty, I should say, to minus, whatever in log? And the reason is highly non-trivial. It's also non-trivial to fix that. The reason is that most of these underlying Bing Gaussian process idea is that you enforce some idea of continuity across neighboring bins, right? The way you do it depends. In Ilya's papers, I think it was more like a radius around the bin. In our case, it's just a next neighboring. And so all else being the same, basically the code will prefer not, changing the rate too much, but keeping roughly, constant. Again, you can do that in a region where if you calculate how many detections you would have gotten with 10 to the minus 9 and 10 to the minus 2, you get the same number pretty much. And so it doesn't have enough data basically to tell you which one it is. Again, I agree, it's not optimal. That's why the paper, the presentation is not called "We Did It," right? Because we're not there yet. There is definitely work to do, but at least we know why it's happening. And of course, I should also say, though, to make it look less grim, is that this is a log scale plot. So in real life, this peak would be massive, and here you would really be splitting hair between 10 to the minus 8 and 10 to the minus 3 or 1.
No, it's more like 5%, right? If you get the area of the curve. Like stuff on the left, to the left of 0 is still about 5% of the peak.
Yeah, fair enough. Yeah, fair enough. Okay. Yeah, so anyhow, we're aware that's an issue. I should say, again, it's an issue that is generic to these agnostic models. Solving is non-trivial. Yeah, please.
Hi, Salvo. Thanks for the great talk. I just wanted to comment, sorry. People have talked about LVK analyses continuously leaving out 1908-14. As you mentioned, you can definitely include it. But there are also strongly parametric models that have for a long time included that event, and it has not been an outlier. Amanda has been working on such things for a while.
Thank you, okay.
Yeah, so it's definitely in there, like it's, it can be accounted for and it kind of in the
Yeah, thank you very much. This, I guess, was captured by my big table. With strong models, you can do these kind of things. Absolutely, yeah. Thank you, Reed. And sorry, Amanda. As I said, now that I have a daughter, I can blame her. So I was not sleeping enough to remember this. Something like that.
Yeah, I was also asking about 1908-14. I didn't know about the part where it's not considered an outlier, so thanks for that. But when you included and excluded 1908-14 in your analysis, did you find any differences in what you inferred about the underlying population, and did you get a different rate estimate for highly asymmetric?
I mean, as you guess, from the fact the uncertainties are so large, the answer is no. I should also say Sophia's produced this plot for me yesterday. So I don't have all the answers yet, but based on the uncertainties, I would say no. Okay, so to me, this is more like, we use 1914 as an example because it was an event that, now reads, caveat notwithstanding, it was a bit always, an outlier. You have to treat it in a special way. So it was the first thing to try. But in my opinion, the most promising, idea behind something like this is that the pixel pop part could capture the correlations that your strong model is not able to capture, or outliers or glitches, right? Aditya is here, right? In Aditya's paper, not Aditya's fault, but they probably have 6 or 7 events which are not astrophysical, right? If you consider the false alarm rate, if I remember the math. Yeah, the VK paper, yeah. But I said, not your fault, right? You were just shepherding the paper. And so, given the false alarm that we expect, that we work with, we expect a certain number of non-astrophysical events. And again, so the idea is that this to me can be a safety net, or one way you can use it. I don't know who was first, is it Vicky and Like?
I think I was first.
Okay.
Thank you for a great talk. I very much sympathize with we need to do this correlation things, high-dimensional correlations. But I was wondering if you could comment a bit on steep or sharp features.
Oh, yeah.
Because, as the other previous plot shows, that you have before, it's probably underperforming there. Or it will always be hard to find these things. And, well, thinking of, say, apparent stability gap or something, whether you believe that or not, how many detections do you think you will need before such a model will be able to capture sharp edges like that, or will it always be a bit difficult?
Okay, thank you. So it's fun that you will mention this because we are obviously working on that. And hopefully have a paper in time scales or weeks. And so it's a great question. So of course the first concern we had when we saw this is that, yeah, but what if there is actually something sharp in the universe, right, a mass gap? And so I don't have an answer for you yet. I can tell you what we are doing, and next time I come to the Netherlands, I'll give you the answer. We are basically simulating our way out of it by simulating universe with or without mass gaps of varying degrees of steepness, and then compare the output of a variety of strong models, like the ones beyond West's paper or others, and the pixel pop, right? Because we're aware of this, we want to be sure that if we did it this way, we would not fool ourselves into believing that the gap is partially filled, for example, when it's not. I don't have the answer yet. Sorry. We should have organized this workshop in 3 months. Yeah. Vicky?
My next. So first, a clarification question, and I should know because it's our collaboration results. But QChi effective, I thought in the 4A catalog, it's not there with
Sorry, couldn't you over?
I'm sorry, QChi effective. We're not finding it with non-parametric models.
It depends what you mean by not finding. Again, Aditya, correct me if I'm saying something wrong. I think it's just more complicated than it used to be. It's behind.
It's definitely more complicated, and I thought.
Yeah. Sorry.
Yeah.
There it is, right? So the non-linear model here would be the spline, unless you have something else on mind.
No, but spline. Yeah, I think there was a bin Gaussian process analysis.
That is possible. Yeah, do you want to comment?
Yeah, and I think there. But I just want to make sure because my sense is that the QChi effective correlation is more uncertain.
Oh, definitely
than it used to be.
Absolutely.
Because I heard you saying it's confirmed, while in my head, I'm not sure it's there. So
no. By confirm, okay. Let me say, I think that this summarizes what I think. I think something is evolving I also said, Vicky, that again, the blue curve does not exclude zero, which is no correlation at all.
Yeah.
Okay, absolutely.
Okay.
Now, we'll confess, maybe we're in a similar boat. Sorry, Aditya, I've not read the 40 pages of appendices, so there may be more results.
Yeah, that's why I'm apologizing, because maybe I missed something. Okay, can I ask a second question, actual question? So you talked, so I mentioned bin Gaussian processes, and you didn't mention it in your list of agnostic models. So Anaria, how is Anaria's work with where they did 3-parameter modeling, and how is it different from Pixel Pop?
I think,
Because they did 3-parameter modeling in 2024, M1, M2 Chi effective.
Okay, yeah. So I think the main, so I do have an area, I don't know if I have the 24 paper in there. So I should say, an area is definitely, so for those of you who don't know what we're talking about, that is the code behind this, pretty much, this kind of results, right?
BGB, yeah.
I think the main difference, Vicky, is how things are actually implemented, and because they're all based on bin Gaussian processes under the hood. And what makes a difference is what kind of basically, neighboring, smoothing, or autoregressive prior you assume. Basically, what you assume about what this bin knows about the other bins. And the reason why that makes a difference is that depending on how you do that, that affects the speed, and the speed affects how many bins you can use, right? Because the computational cost scales with the number of bins that you have in your parameter space. And that is the main reason why, again, especially because Jack is applying for jobs, ask Jack, email Jack for the fully technical explanation. But that's the reason behind why we can do this in a much more finely grid, is because of this conditional autoregressive prior, which is a mouthful, but basically implies that in our bin Gaussian process, every bin is only affected by the adjacent bins, while in other approaches, I think also in your original paper, there is more of a radius that extends a bit farther, and that affects the computational cost of inverting a matrix that is needed to normalize in your rate.
Okay, thank you.
Correct me if I'm wrong, but I think that's the idea.
Okay, just a quick comment. I don't think we had results about the Q-Chi effective correlation from the BGP models in the paper. I guess you're just referring to Anaria's work. Maybe what you're thinking about is the mass redshift correlations, where we don't find any evidence from with the bin Gaussian processes.
Actually, thank you for saying this. Maybe I should have said this. Even though I focus on Q-Chi and M-Chi, because we have some non-trivial results for those, in the LVK paper, we have looked at other pairwise combination, namely M and MZ. And
MZ and M-Chi as well.
And we have not found anything, screaming. Ilya, are you next?
Yeah, so, I mean, one thing that I have to say scares me a little bit about a lot of these plots, and they're very nice results, but I find it scary that we're looking at sort of results that are already outputs of large models, and we never look at the original data anymore. And what I mean by that is that sometimes when we actually plot the data, individual data points with the error bars, we see things that don't quite make sense to us. So for example, some 10 months ago, this was before GWC4 was released, Tom Callister showed me the individual data points behind his Q-Chi effective results, and actually the well-measured parameters had exactly the opposite correlation to the one that he inferred for the population as a whole, which I would say should make one somewhat concerned about the inference, right? Because we know that there are lots of other reasons why false things can appear. For example, Q and Chi effective are partially correlated in terms of their impact on the waveform, which might have an impact. Or for instance, you mentioned that in one of your slides that Chi effective seemed broader at larger Z, but of course we know that at larger Z, we're only sensitive to high mass events, because low mass events you can see at large Z.
Yeah, of course.
But if the events have a high mass, then naturally Chi effective is hard to measure because you only have a few cycles. And so are we really seeing that Chi effective has naturally a broader spread, or are you seeing that the measurements are more uncertain at high redshift?
Yeah.
So I think it's really useful to look at individual data points too.
Yeah, so okay, so a lot there. So first of all, I agree. Of course, there are caveats, maybe not for those parameters specifically, but for other parameters there may be caveats because we have more of a, selection function if you look, for example, at the masses, right? But for Chi effective, definitely. Now, I'm not sure what plot Tom's you're talking about. I was involved, so I'm a co-author of Callister et al. Because we were aware of, for example, the fact that, you know, in each source waveform, Q and Chi are correlated, we did do a software injection campaign to check that if we inject a population that does not have that correlation, we don't get a spurious one. Same in the paper with Sylvia about Q and Chi. Now, this said, I agree with you, there is always a non-trivial element of I just have less data, or, you know, lower in spirals or whatever. That's, again, as I said, I like that the LVK has put a line here that tells you, okay, here you should not really believe those results very much. I agree with you. Ideally, we should do both. I don't think we should take anything, you know, blindly, like, okay, that's the result, I'm going to bet my life on it. I think we need to have a good, we should be like more like foxes than hedgehogs. Yeah, although I do like hedgehogs, so it's conflicted there.
Anyway, I know there's more discussion, but we do have to wrap up so people can
Thank you.
with us. So yeah.